Our next speaker, we have Aaron S. Rinehart, the co-founder and CTO from Verica.io. Aaron has spent his career solving challenging engineering problems for organizations such as United States Department of Homeland Security, DHS, National Aeronautics and Space Administration, NASA, and the Department of Defense, DoD. Aaron has been expanding the possibilities of chaos engineering in its application to other safety critical portions of the IT domain, notably cybersecurity. He began pioneering the application of security in chaos engineering during his tenure as the chief security architect at the largest private healthcare company in the world, United Health Group, UHG. Rinehart recently founded a chaos engineering startup called Verica with Casey Rosenthal from Netflix and is the O'Reilly author on the topic as well as frequent speaker in the space. His session topic is security chaos engineering in DevOps and DevSecOps.
Thank you. Thank you for having me. I'd like to, here at the DevOps India Summit, I'd like to thank Niladri Chowdhury and the programming committee for having me speak at this year's summit. It's an honor to be among such great speakers and great thought leaders in the business. Today, I'm going to talk a little bit about security chaos engineering and what that is and its relationship to DevOps, things like chaos engineering, complex systems, and how we build better distributed systems. My name is Aaron Rinehart. I'm the CTO and co-founder of a company called Verica, and my Twitter information is at Aaron Rinehart. My DMs are open, so feel free to hit me up and chat me up. So, like I said, I'm going to cover security chaos engineering. By way of security chaos engineering, I'll cover chaos engineering. Some use cases, how you can apply it, some experiment framework, some open source tools. I'll point you to a few of those that you can try. You can check out. It kind of tells you how to write them and build them. But also, I'll walk through an example security chaos experiment and maybe cover some additional examples like in Kubernetes and things like that. Okay. My background prior to Verica, I was the chief security architect of United Health Group. For those not familiar with United Health Group, it's the largest private healthcare company in the world. I was like a CTO for security for the company. That's what the chief security architect role was. I also have a background in space and aeronautics, defense for the U.S. Actually, at NASA, I worked in safety and reliability engineering. I'm a frequent author and speaker in the space. I'm also the O'Reilly author on security chaos engineering. It's the O'Reilly report, as well as the main O'Reilly book on chaos engineering. Towards the end of this presentation, if you stay tuned, there will be links to download both copies of both for free. And I also was I'm also the person behind writing Chaos Slinger, the first open source tool to apply Netflix's chaos engineering to cybersecurity. Okay, so what's this all about? Well, essentially, these breaches, outages, incidents, or surprises. That's a good way to summarize them. Surprises. If they weren't surprised, we would have fixed them, right? But they seem to be getting larger, more impactful, and more serious, and more frequent at the same time. We don't seem to be, no matter how much money we're spending, how many new shiny security controls and solutions, we don't seem to be getting any better at this problem. So why is this? I mean, what are we doing wrong? Well, let's start with an understanding complexity. Well, our systems have essentially evolved beyond our human ability to mentally model their behavior. That's a characteristic of a complex system. There are many characteristics of complex systems, but that is what in particular that makes it difficult is that humans, there's too many things going on, too many actions and objects and things and moving and changing and people. And it's very difficult to keep track of what's going on at any given point in time. that makes it hard for for humans to manage and operate an ecosystem like that. And on top of that, I mean, this is the DevOps Summit, so DevOps is doing a great thing for the world, in my opinion, driving their focus back towards building things better the right way. And I think DevOps in the future is just going to be the way we just build things anymore. But what's interesting though is that now with CI/CD, CI and CD and DevOps and the cloud, we're now building. Actually, including microservices in that equation, we're now building systems that are just so large, changing so often, and it's just the scale and speed are just very hard to keep track of what's going on. If you look at the image on the left here, you'll see all the little dots, and they're all connected. That's a microservice Death Star diagram. Basically, each dot is a microservice, and it shows the web of relatedness. There's a rumor that Salesforce's CRM is over 100,000 microservices. Imagine that, right? Your app is 100,000 microservices. In today's microservice applications start off around 200 to 300 services running at any given point in time. It's pretty difficult to keep track of. So where's all this complexity coming from? Well, like I said, things like cloud computing, DevOps, continuous integration, continuous delivery, microservices, service meshes, circuit breaker patterns, blue-green deployments. But you're like, Aaron, but all these things are good, right? Yes, they're great, right? We're delivering value to the market faster than we ever have before, right? That's great. That's what we should be doing. We're shipping it, right? We're shipping it value to customer. But this software is the nature of the ability to change it is also related to complexity. The more so people like to say, if you just simplify the system, the complexity of the system, that you'll get rid of that problem. Well, actually, not really. It's because in order to simplify a system that's complex, you have to change it. You have to do things, right? And the nature of changing it adds additional complexity. And so really, you're just kind of moving the complexity around. So it's not about moving it, it's about navigating it. So expanding on things here is that what you see on the right here is the OSI model. It's now software. Software is officially taken over the equation. Also, like I said before, software only increases in complexity due to the nature of its ability to change. Software is actually one of the only human constructs that actually changes can fundamentally change after it's been delivered. Additionally, here is that there's no layer of software. There's an old saying: there's no problem in software that another layer of abstraction cannot solve. But at speed, scale, and complexity, we're starting to see that become a problem. So, like I said, it's about learning to navigate the complexity. We do that with chaos engineering. That's what chaos engineering is all about. It's all about continuous learning and being adaptable. And adaptive capacity, having the adaptive capacity to respond and learn about how our systems actually work versus how we think they work. There's a drastic difference between the two. So a great example to think about this is the legacy system. Our legacy systems, those are the ones that make all the money for the company. That's the tried and true, that's the big money maker, but it's also the old equipment, the thing we keep around that we wish we could architect away or get rid of, or move to Rev 2. But how did our legacy systems become such stable systems? Well, I actually proposed that it wasn't always really that stable. And when we initially built it out, the system typically is not stable. So we typically learn about what we didn't know about the system through a series of unforeseen events, surprises, right? The engineers, become competent in how the system actually functions through these events, these outages, these incidents, these issues, and then we fix it. We learn, and we fix. But over time, we really start understanding how the system really works. But the problem with that process is we're learning through a series of customer pain. The customer's not having a good time during those types of events. Chaos engineering, you can think of it as a proactive way when there isn't a problem, there isn't an incident or outage or a problem, of surfacing some of the differences between how the system actually works versus how we thought it worked through a series of questions or hypotheses that we ask the system. I believe when X occurs, I've designed Y to be the response. Well, introduce the question into the environment and see whether or not that is true. And I will tell you, I've rarely ever seen that actually be true the first time. So what we forget, though, is that systems engineering is messy exercise. Real work in this world is messy. And humans, we can't think of messes and complexity and hold lots of things in our heads. So we have to abstract and make things simpler. Well, that's kind of why we over time, we don't remember it's messy, because we try to keep order in our heads. But systems engineering is a messy exercise. So the beginning of a design or an application's lifecycle, we have the plan, right? We've got the resource at the time. We've got timeline. We know we're going to ship. We've got a code pipeline set up. We got our security secrets taken care of. Our staging, our prod. We've got a beautiful 3D diagram of the application. Well, in reality, our system never looks like that. Okay, after a few months. Or even a few weeks, our system slowly it starts encountering issues, right? So the marketing team comes down and says that they got the pricing model wrong. We have to refactor the pricing, or so we go do that, right? Then there's an outage on the payments API. We have to hard code a token, right? Then there's then we forgot to update the certs pre-go live or whatever. These things that we just, we're human, right? Like we're constantly working and trying to interact with the system and keep it running. We encounter these problems. Well, what happens is this is how our system kind of slowly drifts into a state of where we don't recognize it anymore. And you get it over more and more time, the problem persists. So in the end, our systems have become more complex and messy than we initially remember them being. So what does all this have to do with security? I'm getting there. So cybersecurity. So my job, let's say I'm a builder. I've been a builder my entire career, but as a builder, I need the flexibility and convenience to change something, right? That's my job. I'm changing. What I'm changing is I'm getting business requirements from the business to make changes to deliver value to customer. That's my job. Constantly doing that. Constantly working on delivering value towards customer. Well, security is a context-dependent discipline. You have to know the thing which you're trying to secure in order to know what you need to secure about it. So security is kind of forced into a stateful situation. So there's this kind of conundrum here. This divergence that's happening is that because it's stateful in nature and it's context dependent, we're constantly, so as engineers that aren't security are constantly changing the system, moving towards customer value. While security is kind of not changing along that curve. So what's happening is that as the changes are happening, we're starting to diverge. What we're doing with security chaos engineering is we're continually asking the system the question, hey, do you still work the way you originally designed, right? Do you still work can you still do the things that you were designed to do? And what we're doing is we're not creating that feedback loop per se, but we're identifying that the security control has drifted out of continuity before an adversary can take advantage of a simple mistake. So where does chaos engineering fit in the world of instrumentation? I'm a big believer in instrumentation, and all science and engineering depends upon it. But Casey Rosenthal, my co-founder, the creator of chaos engineering at Netflix, likes to break down instrumentation sort of into two loose domains. There's testing. We like to say testing is the verification or validation of something you know to be true or false. You know what you're looking for before you go looking for it. Whereas experimentation, we're trying to derive new information that we previously did not know. We're trying to understand what we really didn't know about the system, gain that additional context proactively, and apply that and fix it before it becomes an issue. So how do we typically discover when our security measures fail? Well, It's typically through some kind of footstep in the sand, right? Meaning some kind of log event, some kind of trace, some kind of alert, some kind of monitoring kind of activity, right? But those are kind of very much after the fact, and usually security incident is launched of some kind, but security incidents are not proactive. They're very reactive, and they're not always not very timely, right? The problem already could have already persisted, and you could be just too late to the game, and the attacker could have already taken what they wanted to take. So what happens during a security incident? Well, in short, people freak out. Okay, in normal outages, people are just not in the right state of minds, but security in particular, like I knew I shouldn't have pushed that code on Friday, or I knew I shouldn't have used that third-party code, or, people, because within 15 to 30 minutes, some senior executive, could be the CEO, comes down and says, hey, get that thing back up and running, we're losing money. It's not about what happened, it's about we're losing money. People are worried about being blamed, named, and shamed, right? And they're worried about losing their jobs, right? And that's not, we cannot learn very well as humans in this kind of ecosystem. Okay, so we don't do chaos engineering in this world. Chaos engineering is not about making this world even more chaotic. It's about actually driving order into it. Okay, so we don't do chaos engineering here. We do it here. Unicorns and rainbows, right? We do it when there is no active war room, no incident, no breach, no security problem, right? We do it when we can have eyes wide open, right? When we're not blinded by the narrow tunnel of an incident, right? We're proactively introducing what we believe to be true about the system in the form of a sort of a test, or experiment. We call them experiments, not attacks. Some people call them attacks. It's wrong for so many reasons to call it that. It's an experiment, experimentation, which is key to all engineering. We experiment. That's how we innovate. That's how we figure things out. And that's what we're doing here, is we're experimenting in the post-deployment world, not really not the build process, but the post-deployment world. Say, hey, do the attributes of the system still emerge correctly, right? After all these changes have been made by all these different services and all these different environmental changes, and does in this case security still manifest the emergent property we expect, or we designed it for? Chaos engineering. So chaos engineering, the Netflix definition, is the discipline of experimentation on distributed system in order to build confidence in the system's ability to withstand turbulent conditions. Okay, or another way of thinking of it is it's the discipline of proactively introducing sort of failure conditions into a system to try to determine the conditions by which a system or service will fail before it actually fails, right? We're proactive. We're not trying to create chaos, right? We're trying to be proactive. We're trying to understand, surface the valuable context in the system that will most likely be a problem if we don't, and learn from it proactively and mitigate the problem before it happens. We can't stop all incidents from happening, but we can get smarter about how our own systems work proactively so they don't cause as many of them. So chaos engineering, again, it's about establishing order, not about creating chaos. We're not breaking things in production, right? That's not what we do. Like, I don't know who originally said that. That's a bad idea. You can do this stuff in non-prod and still learn a lot, but prod is where the most value is in doing it. But don't go around breaking things just to break things, because I'm pretty sure you'll lose your job. So moving on. So there's a couple different books out there. There's original Netflix O'Reilly report. You can get your hands on free from download from O'Reilly and Netflix. There is this book, which is that's the one I told you about. You'll be linked to this at the end. That's the main O'Reilly book, the main body of knowledge. And then here's the Security Chaos Engineering Report, and you'll be linked to that at the end as well. Additionally, I'd love to hear from anybody out there who is doing these practices, because I'd love to document your story in the coming O'Reilly book next year. Security Chaos Engineering. In short, it's no different than chaos engineering. We're just focusing on security use cases in particular. So what I always like to say is, engineers, we don't believe in two things. We don't believe in hope. We don't believe in luck. Okay. We believe in data and good instrumentation. I mean, hope worked in Star Wars, right? But it doesn't work for us. That's not how we do things. So what we're trying to do is understand our system and where its security gaps are, before an adversary can take advantage of them. We're doing that by asking the security conditions, hey, I believe when this kind of condition occurs, a misconfigured port, a vulnerable image in a Kubernetes cluster, a what have you, whatever sort of condition you're trying to detect or prevent, that you can actually still do that on a regular basis, and that you don't expose that and let an adversary take advantage of something so simple. So one of the best use cases, there's several different use cases for security chaos engineering. There's control validation, validating security mechanisms work the way they're supposed to continuously. After the first time you run an experiment and you prove that it actually works the way it's supposed to, then you can repeat it like a regression test. And you can launch these kind of things from like Jenkins or CI/CD pipeline, but it's important. It's important to run them continuously too. So incident response is a key use case because the problem with incident response is that its response is reactive, and in particular, what's valuable about incident response is that I'll expand on that actually in a second. But like I said, I covered security control validation, incident response, but also a very interesting use case that is actually observability, right? Security, software security observability in particular is a very challenging issue. But what we can do is find out proactively, do we have the right alerts and context and data and monitoring? Did it inform us when we introduced this kind of event? Did their technology give us the right data we needed to conduct the investigation, figure out what happened? And could we do that in the time frame that we expected to do that? It can be very, very powerful to proactively assess how valuable your monitoring is and your observability. Compliance monitoring, so every chaos experiment, security or not, has compliance values. So check with your security team because the output of the experiments can be used for audits. So we're coming back to its response here is that, the problem with incidents is they're reactive, and security incidents in general are subjective in nature. No matter how much you prepare, how much money you spend, how much security people you have, you still don't know where it's going to happen, why it's happening, how prepared you really are, and why they're doing it, right? You don't know a lot of things, right? And the idea is well, currently the way we do it is we wait till something bad happens to find out whether our technology and our process and our procedures, our run books actually work. Well, that's not a good time, because remember what I said, people freak out. Well, it's not a good time to learn. So like what we're doing with chaos engineering, security chaos engineering in particular, is we're proactive. It's controlled. We're doing it when there isn't a problem. Unicorns and rainbows, remember? So we can learn and figure out, how long did it take us? Did we detect it? Did the log data make sense? That kind of thing. So, wrapping up here, so Chaos Slinger was the first ever tool to perform security chaos experiments. I, along with the team at United Health Group, wrote this tool. It's now somewhat of a deprecated tool, but it's still out on GitHub. You can actually see the framework for it. There's also another tool coming out in the fall for Kubernetes that does some very similar things, as well as there's a tool called CloudStrike, written by Kennedy Chikura, that also does. Also, you can look at to sort of guide your writing your experiments. But in general, you can write these things yourself in Bash, Python, Go, whatever language you choose. You don't need a tool to do it, but Chaos Slinger and CloudStrike and the other tools will give you a model for building it from. So here's a quick example, is that, so the first ever experiment we released for Chaos Slinger in the open source repo was what we call Port Slinger. So Port Slinger was, we need an example that, a software engineer can understand, a network engineer can understand, an executive can understand. Everybody kind of understands what a firewall is supposed to do. Everybody kind of understands what a port is, and everybody kind of understands, that happens all the time. Misconfigured ports happen all the time. Still, for some reason. Go figure, right? Well, it could be that the reason why it happens is that somebody filled out a ticket wrong, somebody applied the change wrong, somebody didn't understand flow, the network flow, and how that worked. Somebody put the wrong ports, many different reasons why that could manifest. Anyway, so what Chaos Slinger did is it pseudo-randomly picked a target amongst a security group in EC2 that was tagged for chaos, because we use reference tags that opt in certain elements. So that's a great way to control blast radius, is have an opt-in tag. But what we do is we either open or close a port that wasn't already open or closed. And what our expectation was as a security team is that our firewalls immediately detect and block it, be a non-issue. So we started running these experiments, in different cloud environments at the company. And we started finding out is the firewall was only detecting and blocking about 60% of the time. And that was shocking. The problem was actually due to a configuration drift issue between our commercial software division and our non-commercial software division. We're very new to the cloud. We're still figuring it out. But remember, there was no breach. There was no issue. We proactively fixed this issue. It was not a problem. So the next thing we learned was the cloud native configuration management tool caught the change and blocked it every time. So something we barely expected to do anything, or at least in terms of catching it, caught it and blocked it every time, which was great. So the second thing we learned. Third thing that we expected to happen was both the environment, the configuration management tool, the firewall, to provide good log data to our security logging, central logging service. We had our own. We didn't use a SIM, what they call we didn't use a SIM tool. We used our own security, our own homegrown version of it. But so I wasn't expecting actually the alert to get fired and correlated from the events, because brand new to the cloud, it's kind of a homegrown solution. I don't know if we built that kind of functionality yet. But what's actually interesting is it did correlate alert, it did generate alert to the SOC. SOC analysts got the alert but couldn't tell where it came from. They couldn't tell which AWS instance it came from. Now, as an engineer, you can say, Aaron, you can map back the IP. Well, true, but that could take 15 minutes, 20 minutes. If SNAT is part of the equation, it could take an hour potentially, because it hides the real IP address. So, but if your downtime's $10,000 a minute. In the case of United Health Group, like during open enrollment, that's like $1 million a minute. That's very expensive. But guess what? There was no outage. There was no loss of money, no loss of revenue. There was nobody to be named, blamed, or shamed. Proactively figured out, hey, all we had to do is add metadata pointer to the event. That's it. Problem solved. But we did all this proactively and safely, and we're able to, fix this before it manifests into real problems. That's the value of this stuff: is the proactive and learning instead of learning through the chaos, where you're constantly reacting to problems you couldn't foresee. That's the end of my presentation. Here's the link to download the Security Chaos Engineering O'Reilly book, as well as here's the link for both. I want to thank everyone for attending my session and the programming committee for having me, and thank you very much.